Hello everybody. What we're going to be looking at today are power series. This is kind of a transition into a new topic that we're going to be doing called Taylor series and Maclaurin series, but we have to go through power series on our way there. Let's go ahead and get started. So what is a power series? A power series is a series. Actually, let me rephrase this. A power series, I want to say centered at x equals a, because they have a center, and that's part of the definition. So a power series centered at x equals a is a series like this, C0 plus C1 x minus a plus C2 x minus a squared plus C3 x minus a cubed, and so on. Okay, that is what a power series is. Now, what are the C's? What's the A? What's all this stuff going on? So the idea here is that the C's, so all of the Cn's, so C0, C1, C2, etc., are just numbers. Real numbers, I should say, are any real numbers. They could be all zero. That's fine, you know. So if they're zero, then that just means some of these terms don't appear. But they're just any real numbers. A is a real number. It is the number where the power series is centered. And the x is a variable. You're actually going to see that in the formula as an x. X is a variable. So if you don't have a variable like that, then it's not a power series. Okay, it's just a series. So what does a power series look like then? Well, I guess first of all, what I want to do is I want to say that we can kind of more concisely write this form like this: n equals 0 to infinity, cn x minus a to the n. So that is another way to write it. And of course, that's just the same formula. So looks like so. All right, and that's a power series. Now, I do want to say something here that it's not relevant right now, but it will be relevant, and so it doesn't hurt to just tell you, remind you, I guess. So here's a little fact. You know what n factorial is, right? N factorial is 1 times 2 times 3 times ... up to n. And we've had to use those before. But you'll notice that in a power series, like, we're starting at n equals 0, and they don't want n equals 0 to be a problem or to have some kind of like special consideration that needs to be done for it. So by definition, we're just going to say that 0 factorial is 1. And I don't even think we're going to see it for the rest of the lecture, but still. So by definition, we say 0 factorial equals 1. And that's just so we don't mess up any formulas later on. And again, we're probably not going to care today, but in the future they will. So 0 factorial is 1. All right, so that is what a power series is. So what they're going to do at first is they're just going to ask you if different things are power series. So here's some stuff. Are the following power series? I guess that should be a colon or something, huh? No, I don't know. Semicolon? I don't know what the right punctuation is there. But here's some examples. So let's say I go 1 plus x squared plus x cubed plus ... And I'm just going to write a few, so I'm not going to answer them yet. So just writing them. So I'm going to add some factorials to this one. I'm starting at a different number. Is that going to make a difference? I don't know. We'll talk about it. Have an idea? Let's see, one more. Okay, we are getting there. A couple more of these, and then we'll be done. Well, we'll be done with this problem. Okay, that's enough. All right, so are these power series? And so what you want to do is just really pay attention to what a power series is. And so the Cn can come from anything. So the Cn can depend on n as much as it wants to. So there could be like any kind of formula for n. A formula using n in the Cn part. However, the part that has the x to the a, or sorry, the x minus a to the n part, that there's really no there's not much freedom. And so this, the only thing you can have for your x minus a to the n's are x minus a to the n's. No other kinds of functions. That means only integer powers. I need to not use that color because blue is the color that I have there. Pick a different one. Red. Only, no, because the red's the color I have there. Why is this so hard? Green. Okay, so only integer powers of x. No other functions allowed. Okay, so you just have to be careful. So if I'm looking at this right here, and this first one, is that a power series? Sure, right? That's powers of x. You know, sure, yes, that's a power series. What about this one? This one is also a power series. Okay, now I purposefully did some stuff that was different, right, compared to the previous one. So for example, I started at a fourth power instead of a first power or a zero power. Who cares? Remember, the c's can be any real number. That means that they could be zero. And if they're zero, then you're not going to see those terms. So it's perfectly fine that it starts at 4. And it's perfectly fine that it goes 4, 6, 8 as well, right? 5, 7, 5 and 7 are not there. That's okay. That just means that the c's that go with those terms are 0. And that's fine. Perfectly valid power series, right? And so you're really just looking to make sure that you just have the integer powers of x, right? Integer power of x, integer power of x, integer power of x. That's an integer power of x. It's an x to the 0, right? In the next one, we've got square root x. Oops. We have square root x squared, square root x cubed. That's not allowed. That's not the kind of power that we're looking for. We need integer powers of x. So this does not count. Not integer powers of x. Not a power series. All right. Last one. This one, absolutely not. Like you have an x inside of a sign. That is not allowed. Okay. that's not just powers of x. That's a sine function of x, not a power function. Okay, so those are not power series. And so once you get a better idea of what these look like, it's easy to see. Just basically, if x is not just a power of x, then it's not a power series. You've got a problem. Okay, and so you should be able to tell the difference. All right, let's look at it one more. Is 2x to the n over n a power series? And I'll start in at 1, not 0, because I don't want there to be a divide by 0. So is that a power series? Well, you can write it out. You can write out a few terms, and you can see if it is or isn't a power series. So if we put in a 1, we're going to get 2x over 1, right? We're putting 1 in for n, not for x. And then 2x to the 2 over 2, 2x to the 3 over 3, 2x to the 4 over 4, dot, dot, dot. Right, so that's the formula. And you can write it out if you want, just to see 2x plus 4x squared over 2. I know you can divide that, but I'm not. 2x cubed would be 8x cubed over 3. 2x to the 4th would be 16x to the 4th over 4. I know that divides out, but I'm not. There you go. So is that a power series? Yes. Right, that is a power series. Those are powers of x, and then everything else is just some number. That is a power series. Okay. Now, the thing about a power series is, like every series, we're going to want to know if it converges. But the problem with knowing whether or not it converges is that there's an x in there, right? They all have an x. And so whether or not it converges will depend on what value x is, typically. I mean, there's some series that converge for every x value, and then it doesn't depend on x, obviously. But in general, it does. So what we'll say, so this is a convergence of power series. All right, and so we have a definition, a power series, write that a little nicer looking, a power series, this one, Cn x minus a to the n, well, it might converge or diverge at different x values. So what we say, a power series, well, yeah, that's it. Just it might converge at one x value, but not another. So you need to be able to check. So you need to be able to check convergence, and the way you're going to check convergence of a power series at a particular x value is you're just going to plug in the x value, and then you're going to use whatever series tests you already know. So you don't use anything new here. So if you have, let's say, if you want to determine convergence of, I'll just write a power series here, Cn x minus a to the n at some x value, let's say like x equals x1. I would have used x equals a if it wasn't already in the formula. But if you wanted to determine the convergence of the series at some point x equals x1, all you do is you just plug in x equals x1 into your series. And after you do that, it's not a power series anymore, it's just a series. So then you just use any series test that might work. So whatever series test you like, well, that will work. Okay, and that's all you have to do to determine the convergence of a power series at a particular point. Here's an example for you. Let's take a series. I'm going to say let. I don't know why I'm saying let, but here's a series. So let that be a power series, I guess. I mean, it is. You don't have to let it be. It is. It doesn't need your permission. And what I want to know is, does it converge? Does the series converge for x equals 1? Question mark. Number 2, does the series converge for x equals 1/8? Okay, so those are my questions. And so you have to do each one separately. Like each one is like its own problem. I'm just doing 2 examples so we can see, hopefully in one of them it'll converge or something, and maybe on the other one it won't. I don't know why I numbered those. I'm going to change those to letters here, A and B. All right, so for part A, let's try it. So if we want to do part A here, we want to know if the series converges for x equals 1, what you need to do is plug x equals 1 into your series. So plug x equals 1 into the series. All right, so you do that. So your series, you're just going to come up here and say, well, there's the x, right? So you just put a 1 in there. So you put in a 1, you get 2 times 1 to the n, right? So that's just simply 1 to infinity of 2 to the n. Well, what is that series, right? That series is simply 2 plus 2 squared plus 2 cubed plus ... You should be able to identify that as a divergent series in any number of ways. So you should be able to look at these, first of all, and see that they are not going to 0. The terms don't go to 0. And that means it's divergent. That's one way to do it. Another way would be to say that this is a geometric series. Also, it's a geometric series. And remember how to do this. When you do a geometric series, like the A, not the A from like a power series here, this is the A from a geometric series. The A is just the first term. So in this case, it's 2. And then the R, the common ratio for a geometric series, is you can get it just by dividing the first term by the second term. So it's 2 to the 2 over 2, which is 2. And then you know that a geometric series diverges if R is greater than 1, and converges if R is less than 1. So just recall, right? Geometric series converge when absolute value of R is less than 1, and diverge when absolute value of R is greater than or equal to 1, which it is here, right? Because it is 2. So that's what's happening, diverge. Okay, so you need to just identify that as a divergent series. So the series diverges at x equals 1. That's the moral of the story here, right? So series, what was it? 2x to the n. 2x to the n diverges at x equals 1. Okay, now move on to the second one. So the second one was a different value. What was it? It was x equals 1/8. So we're going to plug in x equals 1/8. So you plug x equals 1/8 back into the original here. Where is it? So it's 2x to the n. So that is going to be n goes from 1 to infinity of 2 times an eighth to the n. So we just plugged in x equals 1/8, do a little bit of simplifying. That is going to be 1/4 to the n. So if you write out that series, it is 1/4 plus 1/4 squared plus 1/4 cubed plus dot dot dot. That's also geometric. And the a, which is the first term, is 1/4, and the r, which is the second term over the first term, is also 1/4. Also, just a geometric series, when it's written like this, whatever the number is inside of the parentheses is the r. You have to, you do have to check the first term for the a, but the r is easy to see by inspection. So r is 1/4. So what's that mean? That should tell us that this is a convergent series, right? So converges because the absolute value of r is less than 1. So there you go. So series converges for x equals, what was it, 1/8? I think it was 1/8. All right, so that's it. So we just determined the convergence of a series for a couple of different x values. Now, that's not that common of a task, actually. So you're not going to be doing it too much. But you do need to be able to do it, because even when you're not doing this type of problem, the next type of problem we're going to do is going to have you answering the same, it's going to have you doing the same thing as part of it. So this process you need to be okay with, the whole plugging in a point and then determining the convergence. All right, so that's checking the convergence at a particular x value. Next thing you want to do is you want to know about an interval of convergence. Okay, so what is an interval of convergence? So basically what you want to do is, like, think about the previous problem. It diverged when it diverged at r equals, no, let me say it again. It diverged at x equals 1, right? Series diverges at x equals 1, but it converges at x equals 1/8. So a natural question is, where does it converge and where does it diverge? Right? We want to know all of the places where it converges and all of the places where it diverges. And the idea and how we're going to write it is with an interval of convergence. So what we say is, if a power series Cn x minus a to the n, let's see, converges for all x in an interval, Now so I can't use a, right? Because I already used a for something else. So I'm gonna use c to d for my interval. And I'm gonna put an asterisk on this, okay? Okay, there's an asterisk on there, which I'll explain why momentarily. So if a power series converges for all x in an interval and diverges for all x outside of the interval, then the interval c to d, another asterisk there, the interval is called the interval of convergence. All right. Now, so that's just the definition of what it means to be an interval of convergence. So the question is, why, what about the asterisk? Okay, and the only reason there's an asterisk there is it's not something complicated. It's just simply that it doesn't have to be that kind of an interval. It could be like C to D this way, 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 or it even could be negative infinity to negative infinity. Okay, so it just can be any kind of interval. And but I didn't want to have to write that in the middle of that definition there. So just whatever kind of interval it is whatever kind of interval that it is. All right, and that is an interval of convergence. Okay, now of course what we need to be able to do is we need to be able to find intervals of convergence. So what you have to do to find an interval of convergence is as follows. Now this is not like, how should I say this? There are a few circumstances in which you would find an interval of convergence in a different way than this. However, this is the way you're going to be doing it, I think, for every problem on the homework that you guys have. And in the next section, we'll have maybe a different way, but it'll be kind of like a special case thing. So this is what you want to do almost all the time. Okay, so to find an interval of convergence, what are you going to do? So you are going to, number one, you're going to use the ratio test or the root test. So we're going to use the ratio or root test, whichever one you like. They mostly work at the same time and fail to work at the same time. So use the ratio or root test and we're going to use it in a way that's a little bit different than the way we have used it in the past. You're going to say use the ratio or root test by saying the series converges if, and then you know that for the root test or the ratio test, that either that limit should be less than 1, or if you're doing the root test, it would be this one, the limit as n goes to infinity, absolute value, no, square root absolute value, an less than 1. Okay, and the less than 1 is because remember that the ratio test and the root tests say that you calculate a limit, and if the limit is less than 1, the series diverges, sorry, the series converges, and if, no, go away Siri, and if the limit is greater than 1, then the series diverges. So less than 1 converges, greater than 1 diverges, equals 1 inconclusive. I'm going to write that in a minute, but that's why we're doing what I wrote. Now, after you do that, what you're going to get is an interval. You'll get an interval. Like C less than X less than D. Okay? But what happens is the C and D from this interval are actually the places where the ratio or root test was inconclusive, right? Like if you replaced this with an equals for inconclusive, that would be replacing both of these with an equals, which would be inconclusive. So what you have to do is a second part after you get this interval, you have to actually check manually x equals C and x equals D for convergence. So you'll get an interval C to D, and then you need to so check x equals C and x equals D for convergence using what we just did, like what we did for the previous example. So you check those for convergence by hand. Or, yeah. Okay. If the series converges for those x values, or C or D, looks like it said chord, C or D, then you add them back in the interval. So you add them to your interval. How would you add them to the interval? Like this, right? Like you have an interval, and if you want to add the C back in, you just do this. And if you want to add the D back in, you just do that. Okay? So that's it. Two-step process. Ratio test to get an interval, but then you have to check the endpoints of the interval. Okay? Yeah. So that's the method. And let's go ahead and try it out to solve a problem. All right. So something that happens a lot, I guess, actually, before we do a problem here, something that happens a lot is that you don't get like C and D both included. A lot of times you get one side included and one side not included, and that's going to be due to alternating series versus non-alternating series. So just, keep in mind, this is just a reminder, some series converge, some alternating series converge, but if the terms were positive, then they would not converge. So if the terms were positive, the series would diverge. And that's just to remind you of the sort of thing that might go on when you're solving some of these problems. So like, for example, this series, actually, let me not do that one yet. This series versus, now I'm going to make them all alternating. Don't know why that was so hard to write. All right, so there's 6 series actually. And if you want to know whether or not they converge, then the top 3 are all P series. And with P series, they converge if P is greater than 1 only. So this diverges because this is P equals 1/2, but this last one converges, right? Because they're P series. But the second 3 series, they're all alternating series. And for alternating series, remember, if they alternate sign and the terms go to 0 and are decreasing, which these all are, then it's going to be convergent. So, alternating series where the terms go to 0 and are decreasing, which means converges. Okay, and so that's the kind of thing that you want to notice, that basically your alternating series, if they're going to go to 0, are probably just going to be convergent. And if you've got P series, then you just decide based on whatever the P series is. Okay, I just wanted to remind you of this before we did any problems here. All right, now let's do a real problem. Example. All right, find the interval of convergence. All right, so simple. I mean, not that simple, but what you're supposed to do is simple. of, and I need a series. We're going to go 1 to infinity, 3x parentheses to the n, that's an n, over n. All right, easy peasy, let's do this. So the way you start this out is you say, according to the ratio test, or root test is actually probably easier here. But I'll do the ratio test. I think the book would do the ratio test. So let's see. By the ratio test, and I'm just doing this on autopilot, right? Like I know that this is just how you do the interval of convergence of a series. So by the ratio test, the series converges if a certain limit is less than 1. This limit, the limit as n goes to infinity of absolute value an plus 1 over an is less than 1. Now for convenience, what I'm going to do is before I even plug anything in, I'm going to rewrite this as the limit as n goes to infinity of an plus 1 times the reciprocal of the reciprocal of an, which is 1 over an. And the reason I want to do that is it's just less writing, saves a step, although it didn't really save a step because of the fact that I had to write that I was about to do it. But if you're consistent, it'll save you a step. So limit as n goes to infinity of an plus 1. So remember what that is. You're going to take the terms here and you're going to replace the n's with an n plus 1. So 3x to the n plus 1 over n plus 1 times the reciprocal of an. So this is an, right? So the reciprocal of an is just that fraction upside down. So n over 3x parentheses to the n. And we want that less than 1. Okay. I think I'm going to come up here so we don't waste so much space. And then I'm going to have the limit as n goes to infinity of, and what I'm going to do is I'm just going to group terms. What you want is terms that look alike above each other. So like this 3x should be above this 3x. And this n should be above this n plus 1. So let's rewrite that. So we have 3x n plus 1 over 3x to the n times, and then I've got n over n plus 1. And all of that should be less than 1. So then we're going to simplify this. So we cancel terms. Like specifically, right, you've got 1 extra 3x plus 1 on the top here versus the bottom here. So you cancel some terms, and what you're going to have is the limit as n goes to infinity of, it looks like it's just going to be 3x, right? Because there's just 1 extra on the top. And then you've got your n over n plus 1. There's nothing to do there. I'm just going to leave it less than 1. Okay, so then what? Well, then what you want to do is you want to actually take your limit. So take limit as n goes to infinity now. And so the main thing to keep in mind is just how you do the limit over here, right? This is first power and this is first power. And so according to the rules for limits there, if they're the same degree on the top and the bottom, you just have to divide the leading coefficients. And the other term here, the 3x, actually has no n's in it at all. So when you take the limit, nothing happens. So the result when you take the limit is absolute value. The 3x is just 3x, and n over n plus 1 goes to 1. Right? 1 over 1, ratio of leading coefficients. So you get 3x less than 1. Okay, so now you have this. So now, that is not how you spell now. Now you have a little inequality here. Okay, what you want to do is you want to split that into what we call a tri-inequality. You do this every time. So this is the first time you're seeing it, so it may be confusing, but you do this every time, so you'll get used to it. So what you do is this. So the idea is we don't want an absolute value. So if the absolute value of 3x is less than 1, that means 3x is less than 1 or bigger than negative 1. And that's how you get rid of the absolute value. So whatever this number is this number. And whatever that number is this number, but with a negative in front of it. So that's not supposed to be like too hard there, okay? You just split it like this. That's how you drop the absolute values. Now then what you want to do is you want to solve for x. So solve for x. Now what does that mean here? That means you're just going to, well, we got room, so I'm going to rewrite it. Negative 1 less than 3x less than 1. So all you're going to do here is you're just going to divide by 3 on everything. 3, 3, 3. You're just using normal rules for inequalities. So we get negative 1/3 less than x less than 1/3. Okay, that's what we wanted. Now look up at my steps for solving this. Right, when you do the ratio test or the root test, I say on step 2, you get an interval c less than x less than d. We did. We got negative 1/3 up to 1/3. But what we have to do is we have to check the two endpoints here, the c and the d, because the ratio test is inconclusive at those 2 points. So we've got to now go back and check for convergence at negative 1/3 and positive 1/3. So we have to check, what's the series? I'm going to write it. 1 to infinity, it was 3x to the n over n. Was that it? Probably. Where is it? Yeah, 3x to the n over n. So we need to check that for convergence at the two values. X equals negative 1/3, x equals positive 1/3. And we do that exactly the way that we did it for the other problem. So you just say, okay, well, let's check the first one, negative 1/3. So you just put an x equals negative 1/3 right there for the x. So you get the sum 3 times negative 1/3 to the n over n, which is 3 times negative 1/3 is negative 1 to the n over n. And then you need to ask yourself whether or not that converges. And you're supposed to know, right? You're supposed to look at this and easily be able to identify this as a convergent alternating series. You don't need to know that it's alternating, in fact, but I mean, if you didn't know it was alternating, how would you know that it converged? I don't know. So you need to recognize this as converging. So converges. Why? It's an alternating series. And specifically, it's a convergent alternating series, but I'm not saying all that. So you just look at it and say it converges. So then you do the other one. X equals positive 1/3. Doesn't matter what order you do them in. Just take your pick. So you put in a positive 1/3. So you start over, which is 1 to the n over n. But of course, 1 to the n is just 1. So this is the series 1 over n. And so you need to look at that and you need to identify that as a divergent series. You could say it's p equals 1, right? That's why. It's also called the harmonic series, and we specifically learned that it diverged. So there you go. Now you put this information together, right? So we know that it converges for x equals negative 1/3 and diverges for x equals positive 1/3. So you just combine that with the information that you already knew. So we would say that the interval of convergence then is, well, we already knew it was -1/3 up to x up to +1/3. And now that we know that it converges for x equals -1/3, you just come over here and you add that equals back in. Or for Newton, right, where they want it in interval notation, you would write that as square bracket -1/3 +1/3 parentheses to include the -1/3. All right, and that is an interval of convergence, right? So they're kind of long problems, right? Like you'll see that took me like the whole page, right? And I wrote a little bit of stuff that's unnecessary, but for the most part, that's just how long it takes, okay? It is what it is. Somebody is emailing me. All right, so I want to do another one because there's some stuff that can be confusing here. So let's try this. Find the interval of convergence for, trying to think here. All right, I think I got it. I'm going to go I don't know actually what I want here. I'm going to go with x to the 2n, because why not? And then I'm going to go n factorial over n. And I need to start at 1. All right, so there is a series. Okay, so that's a series. Now we go through the same steps as we did for the previous problem. So what we're going to do first is we know ratio test says it converges if the limit as n goes to infinity of an plus 1 times 1 over a to the n, right? So I'm not writing it the other way first. I'm writing it the way I'm actually going to write it. So if that limit is less than 1, it converges. So when does that happen? So we put in our stuff. So an plus 1, we've got 3 different n's. We got one there, we got one there, we got one there. I did that because I wanted to make sure we were okay at simplifying different kinds of things. So you have to be careful with how you put in your n plus 1. So notice that you got to use like parentheses there to get that right, parentheses there to get that right. And I didn't need them in the bottom, but I still put them anyway, right? Parentheses to get that properly, to get that correct. Okay, and then we got times 1 over a to the n, which is just the series upside down. So that would mean n factorial on the bottom, x to the 2n on the bottom, and then n on the top. All right, less than 1. Okay, so what was next? So we kind of wanted to group our stuff, right? That's how we do this. So you put all the stuff that goes together. So I want to actually get rid of these highlights. So like I want the factorial to be matched up with that factorial. So we're going to have an n plus 1 factorial in the numerator and an n factorial in the denominator. Then what else looks alike? Well, I've got an x to the 2n plus 1 and an x to the 2n. So that's x to the, I'm going to write that, it's 2 parentheses 2n plus 1. I'm going to write that as x to the 2n plus 2 right now, over x to the 2n. And then we got an n and an n plus 1, which remember that's not going to be a hard limit. Less than 1. So then we got to simplify stuff. And so you got to remember how to simplify things like in factorial. So, you want to recall n plus 1 factorial can be rewritten as n plus 1 in factorial. That's how we're going to simplify that. And also, x to the 2n plus 2 can be written as x to the 2n times x squared, right? Because you would add the exponents. So let's rewrite it with those replacements. So we've got, I don't know why I'm putting equals, it's not equals. The limit as n goes to infinity of, we've got n plus 1 in factorial over n factorial times x to the 2n x squared over x to the 2n times n over n plus 1. All of that is less than 1. So then we simplify by canceling some stuff. So we're going to cancel. Hey, I switched colors and it didn't switch colors. Cancel stuff. What stuff? In factorial, x to the 2n. What are we going to get? Limit as n goes to infinity of, looks like from the first fraction, all we have left is an n plus 1. From the second fraction, we have nothing. Oh, no, we do. We have an x squared. I lied. And from the third fraction, we have n over n plus 1. Less than 1. Well, it looks like I can cancel one more thing, can't I? I've got an n plus 1 and an n plus 1. So I actually have the limit as n goes to infinity of, looks like, parentheses, x squared n less than 1. Okay, now here is where we have a little bit of trouble compared to the previous example. We need to take the limit as n goes to infinity. There are two things that happen. As n goes to infinity, two things could happen. So the first thing is that x might be 0, right? If x was 0, then what you'd be looking at is the limit as n goes to infinity of 0 squared times n, which is less than 1, and then 0 would be less than 1. And since 0 is less than 1, that would tell you that the series converged. So because that's true, right? 0 less than 1 is a true statement. It's true. The series converges if x is 0, right? Because that was what I assumed there. But if x is not 0, if x is not 0, and then you're going to try to do the limit of this as n goes to infinity, you're going to get infinity times x squared, right? So as n goes to infinity, what you get is absolute value of x squared times infinity less than 1, which is infinity less than 1. Well, that's not true. Since that is not true, is false, right? That is not a true statement. I didn't actually write what I meant over here. So I just realized that it says, since 0 less than 1 is true, the series if x equals 0. No, so the series converges if x equals 0. Let me rewrite this over here real quick. If x equals 0, right? Because remember, the whole thing about that inequality was the ratio test says the series converges if it's less than 1. So in this case, it was less than 1. If x is 0, then the series is less than 1, or the limit is less than 1. So converges. And over here we have, since infinity is less than 1 is false, the series is going to diverge if x is not 0. Now, there's no interval. We didn't get an interval, did we? So you need to understand this result and what it's telling you. The result is this. Together, this says the series, what is it? Where is it? In factorial x to the 2n over n? Is that right? Is that right? That's right, right? Yeah, that's right. So this says that the series converges if x is equal to 0, which, think about it, right? If you replace the x with the 0 there, it's just the sum of 0. 0 plus 0 plus 0 plus 0. Everything's 0 if x is 0. So the series converges if x equals 0 and diverges otherwise. So I don't want to say otherwise. I want to say diverges for x not equal to 0. Okay? That's the answer to the question. There is no interval of convergence because there's no interval, right? We didn't actually find an interval because there was no interval to find. Okay? Now I don't want to leave it at that. I want to say a little bit more. So the series, let me just rewrite it here. In factorial over n, right? And then we have the x to the 2n part. So this is the part that makes it a power series, right? Right there, power series. But with the factorial in the numerator, right? With a factorial in the numerator was big. So the factorial in the numerator basically means that the numerator is bigger than the denominator. And as n goes to infinity, pretty much no matter what, except when x equals 0, because then the series is just, if you put in x equals 0, it's in factorial over n times 0, which is the sum of 0, which is 0. All right, so every power series at least converges at one number, because you've always got a term like this x to the 2n where if it was 0, the whole thing is 0. So that can happen. Okay, so you've got a couple of questions that will ask you something about this. They don't ask you for the series, like they don't ask you for the interval if this is going to be your kind of answer. What they do is they make a statement that looks just like what I wrote here. They make a statement that says, they give you the series and they say converges for x equals 0 and diverges for x not equal to 0. And then they just say true or false. And you just have to say, oh, yeah, or no. But they don't ask you for the interval because there is no interval. I asked you for the interval because I wanted to go through the problem. Okay, so that is power series, okay? I'm going to stop this right here. We have one more lecture on power series coming up. Good luck.